That's just a quick explanation to that. So now the spread measures all uh, the way the data are scattered or arranged around the center of the distribution. So number one, what we check for whenever we want to check for spread is a range. Range is the difference between the maximum values and the minimum values we have. It's very important, but it looks simple, but it's very sensitive to outliers. Um, the formula is just maximum minus minimum, just a simple mathematical operation. Then variance measures the average scored distance from the mean. So variance is, I will just tell you the variance is the one that gives us the high level knowledge of how far our mean might be from the median, or how far our mean is from in the is how far our mean from the middle of the distribution. So if you have a very high variance, that means we have some numbers that are extremely high or extremely low that is causing a distortion that is making our mean to go further away from the middle of the distribution, as we see in this diagram here. So there's a high variance here. That means some numbers are pulling the mean away from the center uh, of this distribution. I think that's the best I can do right now, but so this unit, as you can see here, is squared. It's usually the sum of the our entry or the numbers that we have in our data set minus the mean. Then we square it, then we say divided by the total number of entries that we have. So this is squared and it makes it difficult to interpret during analysis. So in that aspect, as a result of that, we have to use a standard deviation, which is the square root of variance. So this one is bringing it back to the normal applicable mode. So, so the moment we square root a variance, we try to bring it back to the same unit as the original data. Then this is a rule of thumb, I mean, a general rule that says about 68% of data falls within one standard deviation of mean. So for every normal distribution data that we have, 68% of the data is within one standard deviation of mean. So about 95% stands between two standard deviation of the mean. So from the left to the right. 95% from here to here stands between two standard deviation of the mean. That means we do not have a lot of outliers around. The outliers will be cut aside here. So that is for normal distribution. You just have to remember that. So for interquartile range, the quarter range is the range of the middle 50% of the data. That means 50% of our data. Uh, do I have it here? I'm not sure I have it here. Here's a box plot. Mhm. So we have it here right now. The AQR is this range of the middle 50% of the data, talking about Q3 to Q1 around this region, Q1, Q2, Q3. So using 1.5 times, this is another standard rule that we use for interquartile range. 1.5 times IQR, this is a standard rule in statistics to find weird data points. So anytime you use a 1.5 times IQR, then minus Q1, Q1 minus that shows you the possible outliers you have at the lower level, Then if you add it to Q3 plus 1.5 times IQR, you have the outliers that are possibly at at the upper level of the distribution. So when you are at the middle, the Q2 definitely here gives you the median value of the distribution. So from here to here is Q1 to Q3, and anything from here upward is to be regarded as a part of the whisker. It's an outlier to, we will start regarding it as an anomalous, and here is the outlier. Here also anything 1.5 times IQR minus Q1 shows us like anything below this is to be required start to be identified as anomalies, and anything outside the whisker area is an outlier. So this is very important. So an outlier is any data point that falls outside those fences, and this is officially flagged as an outlier. So the statistical way of saying it is this point is so far away from the normal middle that we should probably go check if it's a mistake. So any data point that falls outside, far away from the middle, the median, is a data point that is supposed to be um, investigated. So this IQR is robust to outliers and used in box plot and outlier detection. So this is a box plot. We call it box and whisker plot, in case you get to see it later on. So so here we're going to calculate some of our spread and variability measures. Uh, so for a range, like I said, we're just going to calculate the value dot max. So the values are taken from here. For every column, in numerical column, we are checking uh for every data in that numeric column. Here we are putting it into values. So let's say we have quantity here. So quantity is going to be data quantity, then it's going to append it to the value variable. So we are using the values to measure the spread in this code. Here we are, the range value is value.max. That's what you can always get from the series data. When you say dot max, it returns the max, and dot mean returns the mean of this series data. So here is just saying format, a print formatted special prints features shows that we can just say, hey, dude, anything you see here in a curly bracket, try and replace it with a real data. So range value is going to put this range value here. The real value is going to be printed out, and is going to format it in the two decimal places. So this is what this means. And for here, we're going to do the same thing. If you want to check for the variance of a particular series, you just call dot variance, and the same thing goes with standard deviation. So it does the same thing here. This is a format, F-string format type, saying, hey, look into the curly bracket. Anytime you see a variable, replace it with the value of variable and format it in two decimal place. The same thing happens here. Standard deviation formatted to decimal place. So don't be taken by surprise when you see this. It's just a formatting method. Now we have the coefficient of variation. I did not really talk about this, but this you might use or need in the future if you really want to go dive deep into statistical analysis. So it's standard deviation divided by mean times multiplied by 100. So this gives you coefficient of variation. We did the same F-string format here to format it in two decimal places and to give it some other textual values. So then the last one is interquartile range. Q1 we say to start from 25% and Q3 from 75%. So Q3 minus Q1 is the interquartile range. Um, when we run it, for quantity column, we have range, mean, variance, standard deviation, this. The interquartile range is starts from Q1 is 44 kg and Q3 is 113 kg. So anything between 44 and 113 is regarded as normal, and anything below 44 is regarded as um, might be regarded as an outlier, and anything above 113 may be regarded as an outlier for the quantity column. The same thing for price column and total sales column. Now, let's quickly run calculate the standard deviation of total sales. Um, we want to calculate the standard deviation of total sales. Okay. Um, Now we are gonna use before we start, we can just pause it. You remember we did the price per kg aggregation the other time using the mean and median operation. We can also use the same method here. Uh, let's let me see how we gonna do it. So welcome back, and if you pause and you did some you tried your best and you were not able to get the right result, let's just try and do it together. This is an int that was given to us, but I think this int might not I don't want to use this. I want to use the previous method we used the other time for our price stats. So let's just say this is city standard deviation, SCD, and we say we want to group it by data dot group by. Want to group by what do you want to group by? I want to group by city, right? Yeah, by city. Uh, I like to use the aggregate method so that we get familiar with that. Um, Now we say standard says it's got to which column do you want to use total sales and which operation we want to carry out is standard deviation. Yeah, we say we want to reset do we need to reset index really? Mm, Yes, I don't think yeah, we can reset index. If we don't get it right, then we'll come back again. Let's reset index, and before we sort the value, let's check what we are having here first. So it's saying it's giving us it's throwing an error, a warning, not an error, saying the opponent of the reset index. We need to put it as a method. Keep making that mistakes. So now that we have reset an index, now we see city is having a column here and standard sales is here. Now what's the question? We were told to which city has the most consistent sales? So the city with the most consistent sales would be the city with the minimum variation. So how do we get the minimum variation? We need to sort. We need to sort our standard sales, right? Sort value, sort values by what? We want to use by standard sales. In which order we want to go? Uh, we like to go ascending order because we want to start from the, the smallest. Uh, so yeah, we can say in place is equals to true just to save the value into standard into our standard variation. If you don't use this, you can as well just say city standard equal city standard dot sort value. So that's just another method of doing it. But this one has helped us to achieve that method. Um, let's see what we have here. So here we have Accra. Uh, so to get the task. Now we also have which has the most variable. The most variable will be so the most consistent is this Accra, right? We we looked at the index 0. We were able to get Accra. So the most this is the most consistent rather, which is the least variable, but the highest variable is should be we are using iLoc location here to check this Lagos. That's the one with the highest variable. Um, I know this is a lot for me as far as it's a lot, so just take it easy. And here I place a little something a little explanation to explain why we use high location. Here we just use mm, we use the first one. We call the first value um, dot city 0. And in this one, we just say the city iLoc -1. So this is integer location. We're using integer location to identify the last one, which is the Lagos. And we use just normal indexing here to identify the first one. Why do we use HiLoc? So when we use HiLoc here, it stands for integer location-based indexing. This means we are selecting data by its position in data frame or series rather than by its label. Uh, sometimes we could have used the label, but now we wanted to use the integer location. Remember, here it's going to be 0, 1, 2, 3, 4, 5, 6. So if we have put 6 here, I think it will give us Lagos. 7 right there. 7 will give us Lagos. Um, oh wait, 1, 2, 3, 4, 5, 6, 7. City standard 6. This is 6. Nairobi. Oh, so 4 is still maintaining the previous index here. 4 will give us there you go. So here the index is still maintained. But when we uh, the index of the city is still maintained there. But when we use HiLoc, we are no more using the index. We are using the standard integer location-based indexing. All right. Now we'll go through plotting. Plotting basically is just you. I don't know how to say this, but this is you're gonna do a lot of copy and paste when you are plotting. Yeah, that's what I do most of the time because most of the thing is just you just have to change some variables. Like now, here is what we want to do here now. If you see what kind of plot do we want to do is a bar plot. And what do you want to have on your x-axis is city. What do you want to have on your y-axis is standard saves. Which color do you want to have it in is a sky blue. The title that you want to put on top of the chart is this. The plot that you want to have in the X, the label that you want to have on the X axis is city name. While the label on the Y is this. Uh, plot X ticks, I don't know what this is, but we can check it here. Uh, get or set the current tick location and labels of the X axis personal to return the current values. Yeah, just it's giving us the tick locations. Um, I don't really know much about this, so we can read on that and we can discuss on it. If you know, I would love to get it from you. So this plot does show says, hey, we are ready to push our image out there, and here it is. So this is using matplotlib as matplot library. As you can see, this is PLT. The one that we already established when we started calling the module earlier on. You see Accra having the least and Lagos having the highest sales variability. We can also use SNS, which is seaborne. If you remember, we we called on that when we started the module. This module, we call it as a Python module as SNS, Seaborn as SNS. So if you want to use a bar plot on Seaborn, you just say Seaborn dot bar plot. Then the data that you, let's see, so it's here. The data source is city deviation, the one that we already worked on. And the X column is city, the Y column is standard sales. Hue, we do not use a hue, hue order has made a blah blah blah. So you can check more. So these are the labels that you can add as well. And the tick guy also is here right now. I don't know what's doing, but we can read more about that. So this is giving us the same thing that we already had. That is about plotting. So a box plot, sometimes called a box and whisker, which I've shown you earlier on, is like a summary of a crowd. This box plot is very important, especially when you are checking for the overall summary of your data. It's very good for univariate analysis and also for multivariate analysis. Univariate analysis when you are checking a particular column and the characteristics of the column. Multivariate when you are checking many variables and you are trying to compare those variables. So box plot gives you like a very high level overview of this variable. And for the record, this variable is a quantitative variable that you use box plot for, but you can use it to also to compare different categories of the quantitative of their quantitative variable. So the box represent the middle 50% of your sales, the IQR as we have shown the other time. So if the box is tall, that city sales are very inconsistent. Uh, if you have a big a tall box, that means the variance is high. Uh, The line in the middle, that's the median, and the whisker shows the range of normal sales. So there are individual dots which are outliers. They represent high or low sales that don't fit the normal pattern. So let's quickly check the box plot. This is how you go about it. Say SNS box plot, then put your data source. The data that I want to use here is just the total sales. We can check the overall spread of it. Now, so now this is just for the total sales. This is the median. This is the whisker. And we have the box, the IQR here. Um, we can also check for um, using, this is SNS, right? Seaborn. And we can also check for matplotlib library here. So here we are checking for multiple cities. The X is city here, as you can see. Uh, X is city, Y is total sales. So we are checking cities, different cities, categories by their total sales. So this is a very, very insightful chart. At one insight, at one look, you can see a lot of what is happening here. You can see that this guy has a very tall box, which shows that the variability is high. Um, and Accra should have a very short one compared to Lagos. Um, suppose one of the shortest that we have there. Um, Yeah, so that's how you to look into your box plot. I think we should go to the next one, which is understanding data shape. So in our data shape, like I said earlier, we have skewness. Skewness is just measuring the how long tail, how long is the tail to the right of the distribution for positive, how long is the tail to the left or right of the distribution, this depending on the skewness. Is it positive skewness? As you can see here, positive skewness means it's right skewed. That means the long tail on the right, meaning that the mean has exceeded the median. That means the mean has moved from the middle of the distribution towards the right-hand side of our distribution. If you have a negative skew, then we call it a left skewed distribution. That is, the long tail is extended on the left hand side. That is, the mean has gone below the median, and as a result has distorted our distribution such that our distribution moved to the left side of the distribution. What if we have zero skew? That means the distribution is symmetric and we call it a normal distribution. Also, we have kurtosis. The kurtosis just measure the tailedness. It measures if when you have a skew in your data, you have a tail in your data, how long is the tail, how short is the tail. So if you have a high kurtosis, that means you have more outliers that is causing the tail to be long towards an extreme left or extreme right. So if you have a few tails, you call it low kurtosis, and that means we do not have a lot of outliers in our data. Um, how do we check for skewness? We check for skewness if we just call dot skew on our data column, on the column of the data or on the variable. We also, for kurtosis, we say dot kurtosis, and it gives us the value. So we have a threshold. If skew is greater than, if the value of skew that we get on our column is greater than 0.5, then we say it's right skewed. If it's less than 0.5, we say it's left skewed. As we say is symmetric, is a normal distribution. And for kurtosis also, so I remember I said this is just a way to format, so don't get confused. For kurtosis, we compare with 3. If we have greater than 3, then we have a very heavy tails. If we have less than 3, we have a light tail. But if we have um, equals to 3, we say is normal. So for our quantity, we say it's roughly symmetric. Uh, for skewness and for kurtosis, we say it's light tails, fewer outliers. For prices, we have our skewness to be negative, so we say almost negative 0.07, so it's roughly symmetric. Uh, so kurtosis is less than 3. We say it's light taste, fewer outliers, and for this, we say this is close to 1, right? It's greater than 0.5. We say it's right skewed and the cortices is less than, so we say it's light there. Uh, let's quickly see some distributions. I don't want to go through the code now. There's an histogram of quantity. Histogram is plotting the distribution of numeric data and how frequently it appears in our data. So here we say this is a little bit very close to being a normal distribution. Let's see, our quantity, it's roughly symmetric as you can see, and it does not really have a lot of tails. It's light tails here, fewer outliers. How about the distribution of prices? The prices we say is roughly symmetric, and but we say it has also a light tails and fewer outliers. How about for total sales? Now we see that the total sales is right skewed. You see, the tail is extending to this, so we have some high value pulling into the right. And kurtosis, we say it's light tails, it's not really extremely far, so long like that. So, having said that, let's go through some of the box. We don't want to go through the code for now. So here is the total sales box plot as well. You see uh the outliers are well shown here to the right to the top. So you can identify outliers with box there easily. The median value is around here, uh, to 20,000. Um, so that's about it. Now let's move to correlation. Correlation measures the strength and direction of the linear relationship between two numerical variables. Um, we can also say sometimes we check correlation, but with categorical variable, but with there's a method that we use for that. But for this course, let's just focus on numerical variable. We say we use Pearson correlation coefficient, which is how you don't have to worry so much about that. This is advanced statistical analysis. Uh, so correlation typically range from -1 to +1. When you have something that's close to +1, we have a perfect positive relationship. That is, an increase in one causes an increase in the other, or an increase in one leads to an increase to the other. I don't want to use the word causes. Uh, because like we say, correlation does not imply causation. So two variables can be correlated without one causing the other. So, but it's just a relationship that they have. Whenever one goes up, the other one is likely to also be going up if everything is under normal circumstances. So negative correlation means when one goes up, other goes down. When it's close to zero, so there's no linear relationship. 0.9 to 1 is very strong. 0.7 to 0.9 is strong positive. And so same scale also apply in the opposite direction. Uh, Now, let's see from our data set, we have quantity, price, and total sales, and we are trying to show a correlation using heat map here based on the Pearson correlation that we calculated here, these numbers here. So we are trying to create the relationship here for you see out of the list of numbers that we have here, you see 0.76. This is a very high correlation because it's close to, it's a very strong positive correlation. As you can see, that means the quantity of this product has a direct positive correlation with total sales. That means when the quantity of product increases, it's likely, highly possible that the total sales increases, but it's not the one cost. We cannot ultimately or absolutely say that the quantity of a product is the one causing the total sales of the product to increase. Um, we also see that the price per kg as it's is a positive, but not as strong as this positive correlation to total sales. The price per kg has a negative correlation to quantity, but it's very weak. It's nearly zero. So that is not really effective.